On behalf of Professor Zhu Honghu, I will make a brief introduction of Professor Mulligan. Today, Professor Mulligan will bring a presentation, a short course related to the principles and practices in geoenvironmental engineering. And first, I will make a brief introduction to the lecturer. So Professor Catherine Mulligan is currently the director of Concordia Institute of Sustainable Systems, and she is also the distinguished research professor of architecture, civil and environmental engineering in Concordia University in Canada. And she is also the former Concordia Research Chair in Geoenvironmental Sustainability and Architecture, Civil and Environmental Engineering. And Professor Mulligan is also the elected fellow of Academy of Science, Royal Society of Canada, and the Canadian Academy of Engineering, and also the Engineering Institute of Canada. So Professor Mulligan's achievements include the geoenvironmental site recommendation, environmental engineering, and traceability and transport of contaminants. Okay, so she has also published many books and, of course, some well-known high reputational papers. So for the agenda of today's course, we will include those contents. I will not go through them one by one. I think I believe that you all can learn lots from today's content, from the brief content to some in-depth areas that may be your future research areas. And if you have any questions, you can raise it up during the presentation, I think, and afterwards. And I believe that Professor Mulligan is very happy to interact with you related to those questions. And with no further ado, let's welcome Professor Mulligan to deliver today's short course. Professor Mulligan. This one, right?
Yes, that's
okay.
The first one. Okay, so good morning, everybody. Thanks very much for Professor Zhu to invite me. It's very much a pleasure to be here and to be able to give this presentation as well. So I hope it is going to be some informative, and please do not hesitate to at any time to ask any questions. So this information is kind of adapted from the book that I did on my book on sustainable practices in geoenvironmental engineering, which you previously saw as the first one. And then it's also adapted from my course. So this is why the CV 469, 6491 are exactly a course that I teach in the summer at Concordia University. So I wanted to, at the very beginning, just to talk a little bit about what is geoenvironmental engineering and what is needed and what are the different fields involved with geoenvironmental engineering, just to give a start. Look at what some of the contaminants are, where they come from, and then we will look at where they're going, how they move in the environment, and then eventually we'll look at some practices in geoenvironmental engineering to how to manage these contaminants in the environment, and some of the tools that's for monitoring and so on. So the first step, as I mentioned, we'll look at some of the basic stuff. So the idea, of course, is to be able to protect the environment. So we have to work with many people if we're doing this type of work. You have to work with regulators. You have to work with people who own the land, people who are using the land, and so on. The geoenvironmental domain contains sort of a whole range of different disciplines. So you have to know a little bit about soil, the physics and the chemistry of soil, the microbiology. So if you're looking at some of the remediation techniques, they use bacteria. How the groundwater flows, so hydrogeology, and of course some of the chemistry in the water as well. So it's very much a multidisciplinary field. So for me, that's what makes it really interesting for me. So exactly what is the geoenvironment? So the geoenvironment is basically this interface of soil with either the water, so it could be surface water or it could be groundwater, or it could be the atmosphere itself. So basically the soil surface with the air. So it's basically very much these interfaces. And of course you have the interaction with the like trees and animals that are also there, and of course the humans and so on. So you have this biosphere, what we consider the biosphere, the biological content of the earth as well. So basically you have this ground and surface, you have water influences and so on. So you have all of these interactions. So you're interacting with the air, with the soil with the water, and of course the soil with humans and other entities as well. So if we're looking at doing some work or characterization of the soil, we need to specify what type of things that we want to know. We want to, often you need to know what's going on at the soil, what remediation techniques might you be using, be able to compare the different techniques and see which ones might be the best one. There are also some ground improvement techniques that could be used too. And then of course you need some various tools to be able to do the monitoring and do the evaluation of the site to see exactly what you need to do. So to start off with, we will have like what is hazardous waste. So this is obviously what I'm particularly interested in, is how the contaminants will interact with the soil itself. So what kind of wastes are you dealing with? So these can come from a wide variety of sources. It could be solid, it could be sludges, it could be, which are kind of like a bit of a mess. You could have various liquids, you could have various gases, it could be radioactive, it could be infectious disease type of thing, and so on. But the key of what gets our attention, of course, if something is toxic, is it explosive, is it corrosive, and is it likely to cause some danger to both to the environment or to humans. So these are the things that warrant some attention if it gets into the environment, obviously. So as a future, sorry, I'm gonna hopefully not do that too much. So hopefully, anyway, in the 1980s, it started to be some attention to the contaminants getting into the environment. So people started seeing people getting sick because of certain contaminants that were hitting the environment. So there started to be some regulations were starting to be formed, and some procedures were starting to be formed to deal with these contaminants that were getting into the environment. So yeah, there were some really key cases in the 1990s. In the 1990s, it became a really, really big business in the US to have environmental consulting and try to figure out what would be the best thing to deal with these contaminants in the environment. And so it became a big business to do this. So even it's still a big business in the US, maybe something like $23 billion. I think is the most recent thing that I looked at in 2023. And even in Canada, which is much smaller population, but still a very big country, we still have a lot of need for the environmental protection and environmental consulting and so on. So it's something like $4 billion. So, which is actually quite significant considering Canada is maybe about 1/10 of the population of the US. So it's still growing. So it's a job market that still people can get into, that's for sure. So yeah, so as I mentioned, you can have waste come from all sorts of different sources. So waste materials can come from water. It can contain various heavy metals. It contains things like cyanide. So things like from the mining industry typically will be these inorganic aqueous mixes. You can have, like for the farming, you can have various things like pesticides and all of these type of solutions that of course are used for pest control. You can have all sorts of oils, so like the oil industry, of course, anything that they do in the refining. Of course, you have all the maintenance work for cars, say for example, or for railway cars, or for any of these type of things can generate all sorts of lubricating oils, diesels, fuels, all sorts of sludges that need to be dealt with. And you can have all sorts of other things. So even the environmental industry generates quite a bit of waste. Waste materials. So you can have all sorts of sludges from, say, for example, wastewater treatment plants. You have all the landfills, of course, which contain all sorts of solids. And you have all sorts of other different type of things like this. And you could also have organic materials, so particularly from the organic petroleum industry, and maybe some of the other industries like solvents and all sorts of things. So many industries have their very specific type of chemicals that they're going to be generating, and each of them will have their specific things that you need to do with it. So one of the things you have to be aware of course, is once you have an idea what type of chemical it is, what kind of property will be needed, and so on. So as I mentioned in the past, it wasn't really dealt with, the environmental problems. Nobody really thought about it. They just kind of dumped things into the environment and nobody really cared. And that didn't think it had any particular issues. But what was happening is that once you deal with, like, say, for example, have a whole set of drums like that you could see in this type of picture, these type of materials may start to accumulate in the environment and cause some issues. So particularly when the contaminants are very toxic and very dangerous, then you can have all sorts of issues that can start to be occurring. So and of course, sometimes these chemicals don't necessarily stay there. They'll move because it rains and because of I mean, they might evaporate, or because of the, like over time and so on. So definitely the problem is not only there. So what started getting people's attention was there were certain cases in the environment that started getting people's attention. And basically people started, thinking that, well, there might be some correlations with these accumulation of chemicals and then people getting sick. So people started observing some of these type of things, or maybe even birds and things like this. So in the case of DDT, and people started seeing that maybe some of these animals were starting to die. And then when they did some of the analysis, they found that they were in the tissues of like penguins and humans, and in humans. And so these were like very far from where they were actually applied. So it started to be very surprising to people that these chemicals are being found, not anywhere near where the DDT was being applied. They found various cases where you had birds, the shell was not forming properly for the birds, so they couldn't, they couldn't be born properly. And then also you found some DDT exposure that were become to be associated with people's cancers and so on. So this was one of the first chemical that was kind of flagged as being very toxic to people. So of course it eventually ended up being banned because of these health hazards. There were some other cases, such as mercury. Mercury used to be very commonly used for almost as a medication. So if they cure constipation, people would drink the mercury and so on. But then in liquid form it was okay, but when it did come in the salts thing, then it causes some neurological problems, and so your brain started being affected by these accumulation of mercury. And so then, of course, what also happens is that the mercury gets converted to this organic form, so the methyl mercury form, and this is even more toxic than the mercury form. So people started being affected by the accumulation of this methyl mercury in their bodies. So they were paralyzed, they had sensory loss, and so on. And so this is a case in the 1960s where people, and especially again Japan, were affected by the accumulation of mercury. So, so this was another really key case of, you know, the accumulation of chemicals that were starting to have some issues. So yeah, and also the thing is that it passes through the food chain, which is the other important thing. So if it's in some water phase, it'll accumulate in the sediments at the bottom of the lakes and rivers. The shellfish will accumulate some of the mercury, and then the humans will eat the shellfish. So it starts. Okay. So we get back to. So we have another case as the polychlorinated biphenyls. Was the chemicals that basically they're very large, contain a lot of chlorine groups, have a very high molecular weight, and were used because they're stable because they were used for in electric transformers as coolants and so on for the electricity generation. They're also used as plasticizers, carbonless paper, and so on. So because of their stability, they had excellent properties. But on the other hand, from an environmental point of view, the stability causes issues because then it will stay there. So in the 1960s and 70s in Taiwan and Japan, there were some issues with accidental contamination of the PCBs, caused a lot of issues with miscarriages, birth defects, and things like this. So, so again, this was another type of compound that eventually was banned due to the health issues. In the U.S., one of the biggest cases was this what we call Love Canal. So this was near the Niagara Falls area. So basically, what happened was that there was an area that was sealed off. It was used by a chemical company, and so they used to just dump all sorts of contaminants in that particular area. So that was their area, and they just put everything there. So then eventually what happened was they just covered it over with some land, and then they sold it to a school district, which obviously is not a good idea. They sold it for $1. They built a school, they built many homes, and they built the whole area over this contaminated area. So you can just imagine this is not a good idea. So, so in the 1960s, 70s, people were smelling all sorts of chemicals in their basement. They started having a lot of health issues and so on. So they, of course, they weren't aware of why they were having all of these issues and so on. And then eventually what happened was there was a major investigation, and then they found out that there were maybe more than 100 chemicals that were found in the homes of the people in this area. And so eventually what ended up happening is that the government ended up buying out everybody's land. Everybody had to move because it took a long time to convince everybody, of course, that there was a correlation to all of these chemicals and the health issues. And so eventually that did happen. Of course, it was really, it took a long time. And so eventually what happened was that, as I say, they had to buy out the land, people had to move, and then now they've been trying to slowly decontaminate that site. And actually it's still going on. So, I mean, this has been going, as I say, since the 1970s and whatever. And I think, maybe in the 1980s, 1990s is when they actually started doing the cleanup, but it's still an ongoing problem. Oops. Okay, so yeah, so that's basically just a write-up, and it's one of the most widely known examples of groundwater contamination. There were alarming rates of cancer and birth defects in that area. And basically it was because of all the solvents and dioxins that were in this industrial landfill. And so it had infiltrated into the water supply and had also evaporated into the basements of people. So both by drinking this contaminated water and breathing in these contaminants, did people were affected by these contaminants. And so 800 people were reimbursed and moved. And of course, there were extensive legal battles and media coverage on this site. But anyways, it's a key example of, past processes weren't exactly the best practice. So over time, obviously the awareness has been more generated by the 1960s, 1970s of these different chemicals getting into the environment, the potential health risks that are going on to it. And then you have the analytical techniques have improved quite substantially. So, like you could say, well, there's a chemical there, but if you can't measure it, it's hard to prove. So eventually what ended up happening is that these analytical techniques were improved and improved and improved. So now you can, instead of parts per 1,000 levels of contaminants, then you can do parts per billion. And now for many contaminants, you have levels of parts per billion that you can actually detect in water and so on. There were new regulations that were built with the resource recovery, and things like recycling and recovering of hazardous waste was generated. And then of course you have kind of a mixtures of not only of human and natural disasters that can occur at the same time. So as people might remember, the 2011 Fukushima tsunami that killed about 20,000 people. And then of course you had the meltdown of the Fukushima Daiichi nuclear plant at the same time. So you had all of not only you had the tsunami issues, you had all of the nuclear dissemination due to these the explosion of the plant and so on. So there was such a wide area that this occurred. So the red zone, of course, was the initial where all the problems occurred. But then, of course, there's a wide area that was affected both by the dispersion by the water and the dispersion into the air, because you had the explosion and it got transported into the air quite substantially as well. So it affected, of course, eventually settles down, goes onto the soil, goes into the ocean, it gets transported this way, and also accumulates into the sediments as well. So these are another example of as I say, a mixture of human and natural disaster. So we see how, just to start off with, how they're very interlinked. You have this ecosphere with the atmosphere, the hydrosphere being the water, the biosphere being your biological area, and the geosphere, of course, being the soil itself. So these all will interact in different places. So whether you have surface water, groundwater, and so on. So many of the human activities, so whether it be generating energy, producing various products for industrial purposes, producing, getting natural resources such as agriculture or mining. All of these things, these type of activities can have some impact on the environment for sure. We need to have all these activities, obviously, to stay alive. We need food, we need materials, we need shelter, we need clothing, we need all of these things to be able to exist, of course. But of course, you have to do them in a responsible way. So, so all of these activities, as I was mentioned, do cause environmental issues. So just to list a few of them, you can be generating some waste, you can be depleting the agricultural lands of the nutrients and so on in the land. You can be depleting some of the resources in the soil, such as some of the minerals and things like this when you're doing the mining. You could be producing greenhouse gases, depleting watersheds, sorry, and affecting basically the biological diversity at that particular area. So all of these activities will be producing waste materials, doing some runoffs, doing some contamination, and causing some emissions. And so there's all sorts of different ways that these things are handled, like in terms of the waste generation. In the mining industry, you'll have all of these tailings ponds and things like this. So it definitely, how to handle the waste, particularly from mining, is a key issue. So as I mentioned, you have the geoenvironment. So it serves many purposes for humans. So as an agricultural system, for forests, for urban atmosphere, for the urban environment, and of course for aquatic ecosystems as well. And so all of these environment serves as a habitat, obviously, for microorganisms that are needed to do a lot of the process, particularly for agriculture. We need soil, obviously, for growing, for stabilizing buildings, things like this. You have the groundwater that we use for many purposes, for drinking and so on. You have all of the resources for that we're using for hydrocarbons, coal, things like this, for energy purposes, for building materials and minerals and things like this. So all of these are necessary for all of the activities that we need as a human. So yeah, so these are just some of the things, as I mentioned, like industry. They will all generate their own particular waste, solids, discharges, things like this. The urban atmosphere, of course, you have all sorts of activities that are going on in the city, as you can well imagine, whether it be transport of people, whether it be transport of things like by trucks and railway, whether it be things like working and so on. So you're bringing people to different places. And all sorts of things, and of course people living in the city and so on. The farming and agricultural industry, of course, will generate and use like fertilizers and things like this, so they will spread them on the earth, on the ground, to be able to get rid of pests and so on. But of course, if you use excessive amounts, they can run off into the nearby streams, which then can go into the groundwater. And yeah, so in mining, if you have all sorts of issues with waste generation, so I mean, basically in mining, you take out a lot of the ores, but you only use maybe 1/100th of the material itself, because most of the minerals are very dilute in that particular ore, and then so the rest of the stuff becomes waste material. So which then creates, then you have to stock it and store it and whatever, and then you have all of the issues of water treatment and things like this in the mining industry as well. And in the forestry, of course, if you take too much of the trees, it can then cause some issues with regards to erosion. The soil will not stay in the place, and you will lose some of the topsoils. So these are just some of the activities that can occur. So, sorry. So yeah, so things like, as I mentioned, these are some of the different sources. So the anthropogenic is basically what we mean by human things. So all of the things that I just mentioned in terms of industry, mining, waste generation, agriculture, all of these type of things can generate various types of contaminants for the soil, can affect the soil properties, and can obviously add various chemicals to the soil as well. But not only human activities, but you can have various things like volcanoes, forest fires, landslides, floods, and all of these things can also have an issue on the environment as well. So they can, like volcanic ash, obviously can lead to all sorts of ejections of ash and so on. So you have ash accumulating on the soil. With the forest fires, you have the impact of heat, of course, obviously, with the high temperatures from fires. Landslides, floods, whatever can cause various issues related to the transport of various contaminants or the soil and or whatever is in the soil. It can be moving long distances and so on. So a lot of the natural events can also lead to some kind of changes in the soil properties as well. So this just as an example, this is the volcano that's in Hawaii. So much of the island is now, so Big Island is the biggest island in Hawaii. It actually contains more than 25 million cubic meters of lava, and this keeps increasing and increasing over time. And so this lava now covers most of the island, and so about I shouldn't say most of the island, but about 4.2% of the island is covered by the lava from this volcano. So basically by the volcano, you're actually forming new soil once it cools down. So so there's new land that's going into the ocean by almost which is growing quite a bit. So yeah, sorry. So yeah, so again, urban industrialization, resource exploitation, agricultural activities can all serve as sources of contaminants. So we have what we call two different types of contaminants. You can have point source, which is what we mean is like, that exactly what the source of the contaminants is, and you can pinpoint exactly where it is. Whereas the non-point are basically what's spread out over quite a wide area. So it'll be like the surface runoff, say for example, from an agricultural watershed and things like this. So this is what we call like non-point source. But nevertheless, both of these type of sources can impact the environment. So why do we need to care? Well, particular water is very, very precious. A lot of the water is salt water, which we can't directly use. The amount that's fresh water is either in the form of snow and ice, groundwater, and only a small amount is in lakes, rivers, and things like this. So so it's really, really important to protect the fresh water that we have. So just as a quick schematic of the soil environments, you have the soil, you have of course the rain that will occur, which will infiltrate into the soil. You will have the groundwater underneath there, which we call the saturated zone, and of course with the rain being implemented into the groundwater, it will help to replenish the groundwater. So, but the thing is, if we use too much of the groundwater, this will cause issues with the stability of the soil in that particular area. So contaminants can come from many, many sources. We've seen a few of them: dumping grounds, abandoned manufacturing plants, former waste storage areas, disposal areas, and so on. So as I was saying, all of these activities, whether it be industrial, urban, mining, agricultural, they can all generate various types of contaminants, and which can affect the geoenvironment, and which then can affect the resources available and the health of people as well. So as we mentioned, contaminants can come from various sources. So it could come from a landfill that's leaking. So maybe it's not properly designed in the first place, the landfill. So you can have these leachates that come out. You can have people just dumping stuff like this. And so again, you can have the dispersion of contaminants from there. You can have underground storage tanks that can also develop leaks over time because they're getting old, they corrode, and so on. So they can develop leaks. And all of these can eventually impact your groundwater, which, as you can see, is underneath here. So this is an example also from agriculture. So if you have basically the manure coming from cows or fertilizers that you're adding to the soil, you add to the soil, but if you add it in too much quantity, whoops, sorry, it can run off across the ground and into a nearby lake and so on, and then which then can cause too much nutrients to accumulate in the lake and in the sediments at the bottom of the lake, and thus can be enable the algae to grow, which is obviously not very good. Your lake becomes green, and you could potentially have various toxins that can be formed there. So this was just a quick study that we did in one of the lakes in Quebec. And so you can see here that there's not much natural barriers here, and the water was just running off directly from the agricultural land, which is in behind here, directly into the river here. And so you can see here, here's another example where you can see that there's no natural barriers on the side of the river, and all of the soil just ends up. So basically you're losing the soil, you're losing the soil quality, and you're degrading the quality of the river. So then what can happen is you can have these cyanobacteria can be starting to grow, and these also can be producing various toxins, which then can lead to problems with water quality, and of course the danger of drinking this type of water. So, as I mentioned, you have all sorts of sources of contaminants. So whether they're point source, you can have wastewater discharges that are obviously considered a point source. You can have farming wastes that are usually runoff sources, so these are considered non-point sources. But both of these type of things can affect both the soil and the groundwater. So yeah, so many of these chemicals, like the PCBs that I mentioned, are definitely carcinogens for animals, probably for humans. Some of the metals, as you see, for zinc, copper, selenium, things like this are definitely detrimental to humans. They're good at small concentrations, but when you have higher concentrations in the water and things like this, this is not good. And yeah, so basically, you have the waste, as I mentioned. They're usually defined in terms of corrosivity, ignitability, reactivity, and toxicity. And once they're defined as this, it has at least one of these properties. It's considered as a hazardous waste. So these impacts can be on the land, could be on the water, it could be in the biosphere that's in these things, that's in the water or the land, which then can affect the biodiversity in that particular environment. You can have many effects, as I say, changing water quality, too much various chemicals, and just the overall change in the water. And the same thing for the soil. If you have too much contaminants, then it can obviously affect the land use. You don't want to be using contaminated land, for example, to grow your vegetables and so on. So it's not going to be safe. So humans can definitely be impacted by contaminants in many ways. The contaminants can be onto the ground. They could evaporate into the air, and so we can inhale them. It can then get redeposited onto the land when it rains. The raindrops could actually accumulate some of the dust or some of the contaminants that are in the air, and then can bring back the contaminants to the ground somewhere else. So it can bring it to the ground, or it could bring it to the soil, to the water, maybe in a lake or so on, somewhere else. Humans can have contact of contaminants in many ways, as I mentioned, just directly by inhaling it, by direct contact, say, for example, kids playing in contaminated soil, or you can have people drinking contaminated groundwater or surface water. So these are all ways that humans can have direct contact with the soil or the contaminated environment. So obviously we need to protect the people. So there are different types of contaminants. Each contaminant has its own specific properties. I won't go into too much at this point, but you need to know kind of some of the behavior of the contaminant to know how to address and do the soil decontamination later on. So many manufacturing processes produced all sorts of materials, as we've mentioned, whether it be byproducts, whether it be just maintenance of the equipment, whether it be intentional or unintentional leaks, and whether it be like storage tanks, for example, that are leaking and so on. So all of these things can affect the environment. And then finally, you can also have natural things like tornadoes, earthquakes, tsunamis. All of these also can cause a dissemination of contaminants. So if you have storage areas in this particular area, and then you have a tsunami or a hurricane that comes, then you can be dispersing the contaminants all over the place. So definitely the natural aspects have to be taken into consideration. And of course, as the human activities also can lead to inputs into the environment. So yeah, I think I'll leave it at that. And so yeah, so we've started looking at some of the sources. The next phase I'll look at after the break. Basically, we will look at some of the pathways, and then look at eventually some of the types of remediation or decontamination that we could do to restore our environments in the future. So, oh yeah, I just wanted to mention also that there are sources of natural sources of contamination. So say, for example, like arsenic. It's also found in the environment, in the groundwater and so on. So this is a naturally occurring phenomena that's been occurring in many, many, many places. There's been a lot of discussion about why the arsenic is into the groundwater and so on, due to the changes maybe in redox, the oxygen conditions or something like this. But as you can see, the arsenic has caused many issues in groundwater. So people started going from surface water into the groundwater, and then they started having these cancer issues due to the drinking arsenic contained groundwater. So as I mentioned, there are many models about why the arsenic gets released into the groundwater. So there are a number of programs for remediation. I won't go through these because they're very specific for the US, but each country, of course, has their own remediation programs and protocols and so on. So just as a quick summary, in the 70s, 80s, people started getting aware of the fact that there was contamination in the environment. There was starting to be some pollution control exhibited for adding wastewater treatment facilities in an industry, various industries and so on. In the 90s, we started looking at trying to prevent the contamination from getting into the water in the first place. And then we started looking at thinking a little bit more globally in terms of life cycle assessments and so on. So yeah, so looking at the principles of sustainability, we want to make sure that we dispose of waste and things like this in a proper way, reuse waste in the proper way and as best as we can to conserve both the resources and to conserve the environment, the geo-environment, things like this. So I think I will do a quick break at this point, and then I will change my slides for the next part. Yeah.
Okay, maybe 10 minutes.
Yeah. So we will do a 10-minute break, and I'll start in about 10 minutes.
Yeah. Okay.
Yeah, so you can put it.
So we can close the mic.
Okay.
The mic and the camera is on.
Is on? Okay.
Someone.
Somebody is,
Okay, let me check this.
yeah. Yeah.
That should be fine. Okay.
Okay, so. Okay, so maybe just to ask, does anybody have any questions before I start with the next?
I think the last slides, because I think that's the main introduction, not the very complex.
Yeah, not very complex. No, that's the idea to get the basics first. So we will move to more and more complicated, I think.
Go deep.
Yeah, so we will go deeper and deeper. Yeah, so okay, so we will look at, normally what I'll do is I do the chemistry of the different types of contaminants, but I decided not to do that here, but I'll go directly to looking at how contaminants can be transported in the environment, particularly the soil environment. So this is more or less this set of slides. So this will be the next break off here. So, so looking at how contaminants can move in the environment. So once they get in, as we mentioned, there are different ways, obviously through wastewater, through spills, through whatever, how they get into the environment in the first place. But once they're into the environment, how do they move? So really one of the most important aspects of the movement is water. So water is usually the conduit for movement of your contaminants. So basically this hydrogeological cycle is what's really important. Then, so the rain, the groundwater movement, and so on, and how much runoff you have, and so on. These are all the things that will influence the rate of movement of your contaminants. So what will happen is, obviously, you have the spill into the soil, you have the rain, it will impact filter through the soil itself. You will have some runoff, and then some will infiltrate. And then the contaminants will go from the unsaturated zone, which is the top zone of your soil, to the saturated zone, which is basically where the groundwater is. And then the flow rate of your groundwater is going to be the measure really of how fast your contaminants are going to move. So just schematically, as what I just described, you'll have the water going through the soil, through your what we call the vadose zone. So this is basically your unsaturated zone. You have some areas that have water and other areas that do not have water. You'll have the capillary zone, which is basically this buffer zone between your groundwater and the soil. So there's a certain amount of water that you have there. And then you'll have your saturated zone where the groundwater is. And so basically your groundwater will go from higher elevation to lower elevation, basically due to gravity, right? So water goes from a high point to a low point. And that's basically the idea. So yeah, so these are just some of the definitions. The upper surface, as we call it, is the unconfined aquifer. So you have no barrier on the top, the aquitard, where the water doesn't flow very easily, and then you have the layer of clay underneath, which we'll call is kind of, because it's impermeable, it will be a layer that's kind of will define where the water will go. And so all of these things will allow the water to move or to control the flow of your water. So really the basis for groundwater flow is what we call this Darcy's law. And basically this is the rate of groundwater flow in your subsurface. So in reality, you're saying the change in the level of elevation is one factor. Obviously, if it's going from high level to low level, what kind of cross-section, you'll define a cross-sectional area that the flow will go through. And then you have what you call this, basically the slope. So whether it's a high elevation over a short period of time or whether over an extended period of time length, that will also define how your hydraulic flow will flow. So I will show a few equations, not too many, because I don't want people to get lost in the equations and so on. So it's basically your groundwater flow, which is the Q, is proportional to your hydraulic head, the area that your flow will go through, and you have your hydraulic conductivity, which is your K. So this hydraulic gradient is basically dimensionless. The cross-sectional area, of course, is centimeters squared. These are, and the hydraulic head is centimeters squared, and then of course your flow. Actually, this should be centimeters cubed. There's a bit of a typo there. I just noticed that. Anyway, the hydraulic gradient is basically defined. Defined by what kind of rate the flow, basically your slope of the water. So you have your high level to the low level, and over what period of length is that? So that basically will define your hydraulic gradient. So you can use this law basically to over a variety of conditions. There are some assumptions, of course, that you have a bit of a saturation, that you have this laminar flow and things like this. So these are the different things that are sort of assumed that are occurring. You can rearrange this, saying your flow per area is equal to the permeability times your hydraulic gradient. And so we kind of call this your specific discharge rate or the Darcy flow rate. So this kind of it's a little bit maybe not so clear, but the thing is that you can do these in the lab. You can make a column like this. You can have the certain length of the column. You can have the height of 1, your height of 2, and then you can calculate. You have the cross-sectional area as you see here, and then what you can do is you can calculate more or less what the flow rate is by doing the measurements there, because you know your hydraulic gradient, you know your area, and so on, and then you can calculate what your permeability is of this particular column. So this is the kind of the schematic that you would use to be able to do the calculation of your soil permeability. So as I mentioned, the gradient is dimensionless, and because your direction of flow is basically your H2, your H1 minus H2, but this is, and then when you put it in terms of the delta, it becomes H2 minus H1, and you want to make sure that the flow rate, because your lower one is lower than the higher one, and so that becomes negative. So then to cancel out the negative, we have to add another negative here, basically just to enable the cancellations of the negatives. So basically you can put it in terms of the deltas instead. So the point is, when you're looking at the water flow, is the water is what we're interested in. If you're looking at contaminant movement, and so if you imagine the soil environment, you have all the soil particles, and then you have the spaces between the soil particles. But of course, water cannot go through the soil. It can go through only the pore space in the soil. So that's why I sort of have to define what the pore space is actually, so that you can actually see what kind of movement of the contaminants are actually going through the soil. So therefore, we want to consider only this pore space. So to do that, we have to look at the void spaces and the void areas. And so basically, this flow is what we want to determine. So to do that, we want to see what the flow rates are when looking only through the linear velocity, as I say, the average linear velocity. And so you have your Darcy's velocity times your area divided by this area where your cross-sectional flow is. Sorry. so basically your soil, just going back and looking at the concepts, but that is soil is basically air, water, and soil, right? The solid part. But if your soil then is saturated, there's no air part. And so then it only contains the two phases itself. It only contains the liquid phase and the solid phase. So now your total volume is basically this volume of the voids plus your volume of your soil. So that's basically what we're saying there. And then now your porosity, which is basically this pore space, is basically your volume of the voids divided by the total volume of your soil. And so in reality, you're doing something anywhere from 20 to 70% of your soil is actually void space. So depending on what type of soil it is. So you can imagine like a sandy soil will contain a lot of pore space, but if you have a very clayey soil, the pore space is not going to be very large, right? So obviously it depends on what kind of soil it is. So it's also what soil, it becomes very unique, of course, because it's not very uniform and has very specific parameters. So yeah, so we look at so you can deal with it in terms of porosity, as I say, the void divided by the total, or you can do the volumes of your void divided by the volumes of your solid, and we call this the void ratio. So yeah, so your porosities are basically the area, the voids divided by your totals. And so the volume and the area is sort of the same type of ratios. And so since the area is basically your seepage thing and your seepage volume is your Darcy velocity, we can then calculate that velocity divided by the porosity is going to be your seepage velocity. So if we wanted to calculate how fast the water would flow over a linear length of path, so then we would just have to calculate it, the length divided by your velocity divided by your porosity, and that will give you your time. So that's useful, for example, if you wanted to know how long it takes for a contaminant in the water in this part to go to this particular point. So maybe you have a drinking water well further downstream. You want to know how far and how long it will take for the contamination to reach that particular well. So this just gives you an idea of how water actually goes through soil. It's definitely not a direct path. And also the other factor is that this non-direct path also creates sort of like little flows in between. So you get some dispersions that will go on around the solids. So the water sometimes will go here, but then it will kind of have a bit of a mixing that goes on in a while. So it's very complicated in terms of how the flow actually goes through solid particles. Because as I say, the water has got to go where the voids are, not where the soil is. So yeah, so this hydraulic conductivity is what we've been just talking about. And so that's a really important flow characteristic for your soil, because that's a measure of how fast the water will go through your soil. And that's a parameter that's really very important. So sometimes we for example, if you want to design certain things to stop the flow, we will make certain times barriers that are very impermeable in terms of they will have very, very low hydraulic conductivity. Whereas other things, if some other remediation methods, we want a high permeability to be able to allow the water to pass through and to be able to do the treatment properly. So basically the hydraulic conductivity is a very important parameter, in other words. So as I was mentioning, if you have gravel, it's 10 to the 14 times more permeable than a clay is. So you can just imagine, how variable the soil is, so if you have, and then the other unique thing about soil is that one part might be gravel and then the next part might be clay, and then you can have all of these mixtures very, very close to each other. So so it makes the geoenvironment very complex to deal with, obviously. So yeah, so basically also the permeability of sand, as I say, maybe something like 10 to the minus 2 centimeters per second. You can pump, well, using the American units, 10 gallons per minute. If you have a 10 to the minus 1 permeability, that means you have 100 gallons per minute. So you can see basically things change by an order of magnitude. So permeability, so the hydraulic conductivity is not really a very accurate. I mean, you just get an order of magnitude is basically what you need to determine. So yeah, soils are very heterogeneous. Sorry. And yeah, and sometimes you can have various fractures and sand and things like this in the soil because also can make different things. So yeah, transmissivity is another way to look at the movement of through the soil. We can look at as the hydraulic conductivity divided by the thickness of the aquifer. So basically, that will give you the rate of flow in the vertical direction. So as we mentioned, soil near the surface is unsaturated, whereas the beta zone, of course, is full of water. And the zone in between is what we call a capillary zone. So you have a certain amount of pressures that are involved in and so on that will allow a certain amount of water to raise into that level. So yeah, so basically in that particular zone, you have a certain moisture content and so on. And so depending on whether your soil is wet or dried, you can have various behaviors. Sorry. Oops, I think I skipped something. Okay, yeah. Okay. So really what's important, as I've been saying, is the water is the transport mode for contaminants in your soil. So we call the water movement advection. So this is the terminology we use for the if you have something that's carrying the contaminants in a high rate. So like the groundwater flow. As I say, you could have a bit of mixing due to the mechanical means, as I showed in that previous graphic as well. So yeah, so basically your contaminants can be transported by the groundwater. You could have a point source where you have the discrete source. You could also have some dispersions of the contaminants going on over time. You could also have a continuous source of contamination. So for example, if you have a leaking underground storage tank, so you could have, as I say, a 1 point of contamination where you have this, like somebody threw in some contaminants and that's what happened. Or what you could have is a continuous source. So if you have, say, for example, an underground storage tank that's leaking, it's going to continually drip until it becomes empty. So yeah, so you'll have this continual input of contaminants into the environment. Yeah. So we call this the area where the contamination is a kind of a plume, because it becomes like a dispersed area of contamination. And as I say, this could be if you have an underground storage tank, this could be a continuous source of contamination. You can have the lateral spreading. You can have some spreading downwards due to gravity as well. So one of the other mechanisms due to contaminant movement is diffusion. So the contaminants going from a high concentration to a low concentration area. So this is what we mean by diffusion. So a contaminant will be like, okay, you have a source of contamination. So what happened over time is the contaminant goes like, hey, it's too crowded over here. I want to be over there where there's less crowded. So it will move to where the contamination is much less. So it's kind of in that way. And so yeah, so you don't need a hydraulic head, so you don't need any groundwater movement for that to happen. So that is also another potential mechanism of movement of contaminants. So yeah, so there are many different processes that can influence the transport. You can have some movement along fractures in the soil. So basically, it's a preferred pathway. Obviously, if there's a fracture, it likes to go down the fractures. Or it can go just in different directions, depending on the type of thing. So that's kind of shows the flows for fractures. So obviously, if it encounters a fracture, it's going like, hey, this is a wide open area, so I'm gonna go down this path. This is very, very low resistant. So the contaminants will go in this area. Sorry. Okay. So, as I mentioned, water is like one of the things. So the solubility of contaminants in water is very important. But you could also have contaminants such as organic oils, say, for example, that are not very soluble in water. And they too can be transported through the groundwater as well. So these ones are called non-aqueous phase liquids. So these are ones that are not dissolved in water. And so you can have ones that are heavier than water. So they're dense non-aqueous phase liquids. So various solvents like chlorinated solvents will sink to the bottom of the groundwater. And then you'll have other ones which are light non-aqueous phase liquids, and they will float on the groundwater. So things like gasoline and things like this that are very light, they tend to float on the groundwater. So basically the density is the thing, and the transport will be influenced by gravity. So of course the migration will depend, of the light will depend on the slope of the groundwater table, and the downward migration will depend on what kind of zones it will reach to. So these are just a quick schematic of the light non-aqueous phase. This is the groundwater table here. And you could see that the light non-aqueous phase will float on the top of the surface, whereas the dense will pass through the groundwater and will actually accumulate on the bedrock underneath. So this type of contamination is going to be very, very hard to remediate. So whoops, sorry. So these are starting to see some of the modes of movement of contaminants. So there are other things that, so these are some of the things there are some things that will slow down the rate of movement. So if you have absorption on the soil itself, it will slow down actually how fast the contaminants are going to be moving through the soil, because it's going to be sticking to the soil, right? Instead of actually passing through with the groundwater. So, but this can be reversible. So if it sticks in one place, maybe it can de-stick sometime a little bit later on. So, so there are other mechanisms. So things like volatilization can allow the contaminants to be released into the air. So this is really irreversible, because once it's volatilized into the air, it can be go back into the ground. You can have other transformations such as biodegradation that could occur. So again, you will have a breakdown of a contaminant, and again, it won't be in the original form anymore. And sometimes these type of things will actually increase the rate of movement of your contaminants, because maybe it's a smaller molecule now, and so maybe it's easier to transport. So soil itself is basically, as you know, very complex. It's made really as a breakdown of rock material. So depending on what your source rock is, that's what your soil is going to be initially made of. And of course, it's going to go underneath over a bunch of processes like weathering and so on. So you have the rain, the freezing, the thawing, all of these type of things will have an influence on what kind of soil that you have. And on top of that, you have the organic materials that will also influence, you know, what kind of plants that you have in the area. So what kind of organic deposits that you might end up with. All of these type of things will influence the movement of the contaminants, you know, so will make up a certain soil composition. So the climate, the weather, the how much rain is in the place, how much, what kind of heat that you have, all of these type of things will influence the water movement, the type of soils, and so on. So soil, we define it in terms of how much organic contents you have, how much inorganic contents you have. And then we break it down into the solids in terms of what kind of size of particles you have. So it helps to define what kind of soil you have. So whether it's gravel, sand, silts, clays, things like this. So you have the physical particle size, and then you have the actual mineral particle makeup. So what type of clays, for example, are made up in the soil? So is it a kaolinite, an aelite, a montmorillonite? All of these have different types of properties and will influence the movement of contaminants in the soil. And of course, you'll have other components within the soil itself that kind of form the basis. So the soil, oops, wrong way here. You will actually have some metal content in the soil because the soil actually has a composition of metals in the soil, for example, in the base composition of it. So you have to know what's considered the background levels of contaminants in the soil to say, hey, is this contaminated or not, right, to begin with. Oops, that's not very good. Oh yeah, that's much better. Okay, so as I was saying, your soil can have different characteristics. So as you see, you could have a very clay soil, you can have a clay silt soil, you could have a very sandy soil. So these are type of, looking at the percentages of the different particle size, and then you can define what type of soil that you have just based on the soil particle size. So these are usually done by sieves, and then the smaller particle fractions are usually done by laser diffraction methods. And then you can further define it, as I mentioned, in terms of mineralogies. So looking at the type of mineral content of your clays. So whether it's a kaolinite, a montmorillonite, a mica, chlorite, things like this. As you can see that they all have different makeups. And so usually you can do like an XRD analysis to determine what kind of, so X-ray diffraction analysis to determine what kind of clay minerals that you have. So why you would want to do that is because the different types of clay minerals have different characteristics. So for example, kaolinite versus aelite or montmorillonite. So you can see the specific surface area. So the more specific surface area you have, the more absorption capacity you have for that soil. The more cationic exchange capacity, so the more cationic exchange capacity you have, the better the absorption capacity of these soils are. So, so if you have an aelite, as I mentioned, versus a kaolinite, the aelite is going to be a better absorbent compared to the kaolinite. And as you can see, some of the other, this mica is even better than the kaolinite and the aelite and so on. And the other one that was not mentioned in the previous is montmorillonite, because this one we tend to use a lot for landfill barriers and things like this montmorillonite. So, which is exactly why, because it has a very high cationic exchange capacity, a high surface area, and high charges. So it has many characteristics to enable a lot of absorption to occur in that particular soil, that type of mineralogy. So you would want to be using it, say, for example, as a landfill barrier, montmorillonite compared to a kaolinite. Yeah, so the aquatic environment is a little bit different. So looking at a surface water, you have a bit different mechanisms that are going on, because you might have some accumulation of within the plant materials that are going on. You might have some influences of the sun. So these are a little bit different than what would happen in your groundwater environment. So yeah, definitely different environments. You have different mechanisms that can be occurring. So again, your soil is made of air, water, and soil. And the solids are then made of a whole bunch of different components, as we've started to say. You can have the organic components, which are basically plants that have died, animals that have died, and things like this have been degraded, so they end up so this makes up the organic part of your soil. And then you have the inorganic fraction, which is kind of the crystalline, so anything like the clays and things like this, the clay minerals, which we've just talked about, oxides, carbonates, all sorts of things like this form various crystalline part of the inorganic, but then you have the non-crystalline part. So all sorts of oxides of iron, aluminum, silica, and so on. So very complicated components in your soil. So in reality, your soil is made up of a mess, kind of like this. So you have your silt particles, your clay particles, your organic matter, your crystalline particles, your carbonates, your all sorts of stuff. So your soil is made up of a mixture of a whole bunch of stuff. So this is why you kind of need to really characterize it if you want to know the behavior of that particular soil. Yeah. So basically, as we've been saying, is if you have a contaminant coming into the soil, you'll have a certain interaction of the components within that soil, and then that will determine how much is actually absorbed by the soil, or how much will actually it will be leaching and will continue, and the contaminants will continue on further on down the line. So, as we've mentioned, organic fraction of your soil could be anywhere from 0.2 to 3%. Peat soils itself, they're a little bit different because it's really an organic soil. So we don't count that in this area. Sorry. So so you have these degraded components from your organic phases, so humic acids, polysaccharides, all sorts of stuff like that. And anyway, all of these organic materials could actually bind some of the contaminants as well. So you can have some absorption, as I've mentioned. Oops. So wait a second. So the organic fraction in your soil can actually absorb some of these organic materials. So depending, there are a whole bunch of chemistry related. I won't go down too deep into the chemistry here because that could take all day. But there are a whole bunch of different mechanisms, such as these attractive forces, basically absorption, like charges and things like this that can allow the absorption to occur. So things like PCBs can absorb onto your organic fraction of the thing, and this is a reversible process. So meaning, although it's maybe absorbed temporarily, it could desorb a little bit further down the line, so it's not a permanent process. So so this often occurs, like one of the basic and first methods of doing the remediation in the is to pump and treat the groundwater. So if you have a contaminated groundwater, you just pump out the groundwater, bring it up to the surface there, and then do the treatment on the surface. This is kind of like the first remediation method probably that was ever done. It works well to some extent, obviously, because you're removing the contaminants from the area. But the problem is sometimes if you have these contaminants that are absorbed onto the organic fraction, they will stick there for a while. So sometimes it's kind of difficult to remove them. And then that's why sometimes if you're doing the pump and treat, you'll see it works very well at the beginning, and then the amount of contaminants that you're getting might decrease, and you say, hey, yeah, I'm finished the remediation process. But then eventually what might happen is that you might get another spike of contaminants because now they're being released from the soil. So so you can't rejoice too quickly sometimes because it could be a little bit later on that you get the desorption that's actually occurring. So the absorption of the contaminants with the soil depend on many different types of things. It depends on what type of contaminant that you have, the size of it. The larger the molecule, the more likely it is going to absorb. The more hydrophobic it is, the more likely it will be to absorb. The higher the charge, the more likely to absorb. And it also depends on some of the structures. So some contaminants, depending on the structure, will absorb well, and other ones might not absorb so well. So we've started to see some of the mechanisms for contaminant movement. We've talked about advection for being the water flow, so as a mechanism. The diffusion we've also mentioned, because you have the high concentration, the lower concentration. The dispersion, which happens when you have the kind of the mixing in the soil. Capping is a bit different. We'll talk about that a little bit later, maybe. But now we're starting to talk about absorption, as we've mentioned. Precipitation usually occurs like for heavy metals, say for example. And it's also very pH dependent. So maybe at low pHs, heavy metal might be very, like lead or zinc or something like this, might be very soluble. Whereas if you get a pH of 7 or 8, maybe they will precipitate out and be not very soluble. Yeah, and well, biological transformations that will depend on the microorganisms in the soil. So we look at absorption. So this is kind of the basic absorption model. So basically looking at how we have this partitioning coefficient. So you have so much contaminant in the water, and then so much contaminant will be in the soil. So this is just the balance between those two contaminants. So we call this KD as the partitioning coefficient. So it just relates the contamination in the groundwater versus what's on the soil itself. So obviously, if you have a high absorption capacity of the soil, you'll have a lot of the contaminant will be on the soil compared to in the groundwater. Whereas if it's very soluble and will not absorb too much onto the soil, it'll be the opposite. So often we do these type of, we can do like batch test. So take a certain amount of soil, put it in the water, put a certain amount of soil in the tube, put a certain amount of contaminant in the tube, and then you do the mixing maybe over 24 hours, and then you do the analysis to see how much is in the water phase and then how much is in the soil phase. And then you could generate a curve, something like this. So this is the linear type of curve, which is very, very common. But you could also get, other people use Freundlich curves, or other people will use Langmuir type of curves. So the thing with linear is that it assumes that you're going to have infinite absorption capability, which is not going to be the case. There's going to be a case where you'll have a saturation of the contaminant in your soil at some point. So that's what will occur. So that's why you have all of these other Freundlich and Langmuir or whatever. So they kind of make these adaptations that you don't really have infinite absorption to occur. So I think, let me see, how are we doing here? Yeah, okay. So looking at the land use. So yeah, so we're looking at the different procedures for the land use. We need to assess the land plan and things like this, look at their land carrying capacity of your soil. So some of the things are very sort of structurally oriented for the soil, you know, what type of uses that you're going to use for the soil and so on. Are you going to plan to reuse the soil for something else? You know, how can we assure that we have a safe soil afterwards and so on? So this is kind of the procedure that you would want to look at, first of all, to doing your land decontamination and things like this. You want to make sure, obviously, that the land is useful for your purposes. You'll want to make sure that it's going to be healthy, and it's not going to affect the health of people and not going to affect the health of the wetlands and so on at that particular area. And you know, and then you will obviously have to come up with a plan for doing the remediation. So hopefully you'll have a good plan. Maybe it might not be effective right from the get-go. Maybe the remediation plan that you approved might not work. You might not be able to achieve the objectives that you wanted. And then you might have to go back and rethink your plan. So yeah, so it depends on that. So I think that's the end of that particular set of slides. I don't know whether we want to take another little break, I think. And then maybe we can go for the last batch before lunch after this. So yeah, so if there are not any questions, we'll take another little break for about 10 minutes or so. Yeah. So 4. Yeah. Okay, we'll talk about water after the break. Okay. Yeah.
So continue the last section on this morning.
It's actually the opposite way. The smaller particle, smaller particles. Can I see? Okay. So I see there's a question about what is the reason for high absorption of larger particles in the porous media. Actually, it's the opposite way. The smaller particles absorb more. And why the smaller particles will absorb more is because of the higher surface area. So small particles will have a very high specific area for that size of particle. So each of the smaller particles will really absorb much more than a large particle size. So if you have like clay materials or things like this compared to a sand, the clay will absorb just because of the smaller particle size, will absorb much more of the contaminants than a sand will, say, for example. And that's not taking into account the different characteristics of the surface, but just in terms of the specific surface area is basically that main characteristic, which allows more absorption per surface area for small particles compared to large particles. So I hope that answers that question. Yeah. So yes. So thank you for that question. Okay. Yeah. Okay. So we will go to the last section before the lunch break. So I wanted to spend some time on water. So I know we've been talking about the geoenvironment and so on, but water is, of course, a very important part of the geoenvironment. And it's actually kind of really why we want to have a good soil quality, because we want to protect the water quality. And so, as we know, the water contains a lot of ocean. So about 70% of the Earth's surface is water, but it's mainly salt water. So we can't directly use it, say, for example, for drinking purposes or whatever, without doing all of the desalting of that water. So obviously, it's much more energy efficient and so on to use fresh water for all of our purposes. So we have many uses, of course, for drinking, for growing plants, for all these industrial processes and so on. We use water for many purposes, but of course we misuse water for many purposes as well. We use too much in certain areas. We have a lack of rain in certain areas. Water is definitely not is not properly distributed in the world. Sorry, the world. We get way too much rain sometimes, and other places don't get any rain. So so all of these things make it very difficult to deal with water. So we know from the Sustainable Development Goals, the goal number 6 is to have clean water and sanitation for all, basically. But this has definitely been a challenge, and still been a challenge, of course, in many countries. And in particular, because there's so little of the fresh water is actually available as river or lake water. Quite a bit is groundwater, of course, which is you have to dig a lot. You have to have some deep wells in some cases. Some of it's snow and ice in terms of glaciers, and so some of it is permanently frozen. Of course, this fraction is changing a bit due to the climate change. So there's a bit more shift now sometimes in some of the melting glaciers and melting ice caps towards more fresh water instead. So we know that through the hydrological cycle that the water moves through the environment. So you have the rain, you have the runoff, you have the infiltration through the soil into the groundwater. You'll have some evaporation from the lakes and the rivers. You'll have some surface runoff, of course, into the lakes and the rivers, into the oceans. And so all of this cycle allows for the water to move through the different fractions in the soil. So of course the soil, as you see, has a quite substantial effect on the water quality, obviously. because it will affect the groundwater and the surface water through the surface runoff. So of course, humans mess around with all sorts of things, and of course we've been doing a really good job of changing the Earth's surface. Just something simple like building a road, it changes the infiltration of the water in that particular point. So the water can no longer infiltrate through the road directly into the groundwater. So it'll either be, it'll either go somewhere else as a runoff somewhere else, or it will be diverted as a culvert somewhere else and be taken somewhere a different place. We compact soil surfaces, so we have less permeability of the soils. We contaminate the water and the soil. We can take too much groundwater sometimes. You know, we do the harvesting, of course, to get for various purposes. We use groundwater, and then also we have leaking sewer systems that can bring water into areas that were not originally having a lot of water. Using geothermal energy sometimes can change the characteristics of the heat in that water, and various other aspects like that. So, and of course, agriculture, we use a lot of different additives. So we can add, you know, like various sewage sludges, compost, fertilizers, pesticides, manures. So all of this to add various nutrients. And if we don't add them in the right quantity, we can have too much runoff into the water and create certain water contamination, or going into the groundwater and create contamination as in terms of nutrients. But you can also have the bacteria as well from the animals as well, can infiltrate into surface water or groundwater contamination as well. So this is just a runoff from a mining area in the UK. Actually, this shows you the iron that comes off into the groundwater. So we can see that it's obviously not very aesthetically pleasing. Iron at a certain concentration is also not very good for your health. And actually, I have a groundwater system in the house that I have, which is outside the Montreal area. It's I use the groundwater there because we have no central water system, and it actually looks quite a bit like that because there's just so much iron in the water. So I have to put a whole water treatment system before I can use the water for my for use in my house. So so as you can see, this is some of the problems of lakes and things like this, whether it be dioxins, pesticides, pathogens such as the bacteria, as we've mentioned from animals, things like algae growth, PCBs, too high nutrient concentrations, and mercury in particular are some of the major components that are in North America for and things. And I recently did this survey because this was done in 2014. I recently did it for my new edition of my book, and I think that things have not changed actually very much over these past 10 years. So, so basically, whoops, okay, wrong way. So if you have a contamination, you have, this is where the contamination is. What will eventually happen, as I've mentioned before, it will become dispersed. You have the movement of the groundwater through the contaminated area, so it will carry the contaminants. So that basically, as you'll see, it spreads out the contaminants, and you'll have both the spreading out of the contaminants because of the groundwater and because of the diffusion, because you're going from high concentration in this area to the lower concentration areas there. So you have, in addition, this diffusion as well. So to be able to get an idea of, you know, you need to set up monitoring wells in the groundwater to be able to see where the contamination is going. You set up a sort of a control behind. So the groundwater flow is this way. So obviously your contaminants are going to be going the same direction as the groundwater flow. So your contaminants are going to be going this way. So you can set up a back one. This is kind of a control thing there, sort of to show you where it's clean, hopefully, in terms of no contamination. So you shouldn't have any contaminants in this black one here. And then you set up sort of side ones there to as it spreads out. And then you'll set up some downstream also to see. So basically, you're trying to get an idea of how the contaminants are going to be spreading out in a wide fraction and then over the length of the groundwater. So the idea is to have as many groundwater wells as much as possible to do your monitoring, which you hope to do. So usually the trade-off, though, however, is that putting in monitoring wells is expensive. So companies, if they're doing the remediation work, they will try to minimize the amount of wells that you do. So you have to make a trade-off in terms of what information you want, as opposed to what information you're going to get, you know, because of the costs, because it's very expensive to put in wells, particularly if the contamination is deep. So yeah, so this shows you also, so the previous one was on top, looking at the contamination, and this is a kind of a side view of the contamination. And so if you have multi-level sampling wells, they'll give you an idea in terms of along the depth of where the contamination is in your groundwater. So that's the whole idea. You want to be able to see what's happening to your contaminants over time. So there are many techniques that are done. Obviously, the monitoring well is the key one, because this is the well it's going to be giving you the samples. You could do soil sampling, which I will mention. I will do some. I think the next set of slides that I'll do after the lunch will be on the sampling methods. I won't touch on the remote sampling too much because that's not used too much. Sorry. And anyway, so you get the water samples, you then have to analyze it. The same thing with the soil samples, you'll have to analyze it. And so there are obviously various techniques. So for example, in my lab, I have ICP-MS. We can monitor in the groundwater very, very low levels of arsenic, say for an example. And if you're doing soil samples, often what you have to do is digest the soil and then do the analysis for the thing. So usually soil analysis is a little bit more complicated than the water analysis. Biomonitoring which is using plants or species to see what contaminants are there, is not used so much. So there are various approaches for dealing with the soil and groundwater treatment. I'll start with the ones that tackle the groundwater in this side of the section. So you can do either ones that will temporarily isolate the contamination. So you're not really doing anything, you're just kind of blocking an area that the contamination will stay. So if you're doing like an isolation or containment method, this is what you're doing. Basically, you're not doing a treatment, but you're trying to protect maybe a downstream groundwater well or something like this. And then other techniques will actually do the treatment. So extraction, electrokinetics, natural attenuation, like I mentioned yesterday, using all the natural processes in the soil. Using some as a kind of a boost to the natural attenuation, what we call enhanced natural attenuation, or doing some in situ barrier. So like you could do like an absorption. They have these in situ permeable barriers that, say for example, the University of Waterloo in Canada is very, very, did a lot of developments in this area. So as I say, you could use various techniques. So you can try to minimize the contaminant transport as much as possible. Basically trying to control the flow of your groundwater so that you can control where the contaminants are going. So the idea is that you can put in various barriers, and these barriers will be not permeable. So this is the first approach, so basically trying to cut off the contaminant movement. So you can do these cut-off walls or grout carriers or sheet piling, things like this. So basically, you're just putting like a barrier in the groundwater to stop the groundwater flow and hence the contaminant movement. So that's the idea. And then what you can do is maybe combine it with a pump and treat, so you can pull out the groundwater in that particular area and then do the treatment afterwards on the soil surface. So there are various ways you can do it. So you can take your contaminated area, put these walls around, and so as I say, the whole idea is you're putting up these barriers. You're not really doing anything. It's not a treatment. You're just kind of isolating the area and preventing, like for example, the groundwater from going through that area and bringing the contamination elsewhere. So you can totally surround it, or you can just do a upstream block or a downstream block. So these are different types of approaches that can be used. So again, you're just trying to minimize the groundwater contamination going somewhere else. So yeah, you could also do kind of like if you have like the light non-aqueous flow, as we mentioned before, it will be like a floating product. And you could also set up like a vertical barrier like this, and that would also help to reduce the movement of if you have a case like this. So these are just type of barriers. The idea is that the hydraulic conductivity of those barriers is going to be really, really low. So that's what you're trying to do. You're trying to block the flow. So basically, if you have a hydraulic barrier that has a permeability of something like 10 to the minus 7 centimeters per second and lower, you're basically almost reducing the flow to a very minimal amount. And yeah, so that's basically the idea. You're just trying to slow down the movement. So it's not a treatment, but it's a way of controlling where the contaminants are going. So the most common one is using like a soil bentonite system. Sorry. And so basically you just make these mixtures. You build a trench. You put this viscous mixture of bentonite with water, and then you're basically putting a wall into the system. So as we mentioned before, bentonite is it's basically morilonite. So as we mentioned, I don't know, in the first or second section, morilonite is a very small clay, very high specific surface area, very high charge, and has a lot of absorption capacity. So this is why you choose this type of material to be used as a barrier. And the flow rate through this barrier would be also very low. So you can do this up to maybe 30 meters. Basically, you put a trench there and just fill it with this material, and then backfill it with soil. Yeah. So as I was saying, the permeability very low. So there are different ways that you can do it. You can the trench method is one of them. You can make do types of things like this. You can excavate the soil, put the slurry in, put in these reinforced soils, put in these other type of things. So there are all different ways that you can make these walls. And so the whole idea is basically put a wall into the soil so that you're blocking the contaminant movement. So there are all sorts of schemes that you can use. You can like put in this cutoff wall, just this kind of method like this. So it's a vibrating method. You can use a drilled method like this, like a kind of mixing panels. You can put sort of like geotextiles, also mixing the geomembranes with also the soil bentonite. So they're all different combinations depending on the depth, depending on the width of the wall that you want to make. Yeah, and you can even do biopolymers. So there are all sorts of types of things that you can put in. So depending on the cost, the depth, all sorts of things. If you have fractures in the soil, maybe, as we mentioned before, the contaminants like fractures and like moving along fractures. So if you can stop these fractures, can fill them up with all sorts of grout, that also will help to reduce the movement of your contaminants. So basically all of these barrier methods are what we call like passive methods. You're not adding any water, or you're not, pumping anything. So they're very passive systems. But there are other systems, as we've mentioned, you can that actually are treatment systems. So you have to add energy, and they can be used to do an active treatment. So things like pump and treat, electrokinetics, bioremediation, soil washing, soil flushing, all of these type of things are active type of remediation methods. So the pump and treat was kind of the one of the original methods ever used to do the treatment. So basically you have a well, you put the well in, you pump out the groundwater, and then you do the treatment, sort of really standard water treatment processes. So like absorption, biological treatment, air stripping, any of the biological treatment methods that you want to use. And this is usually done on the soil surface or in some kind of plant. And so you then have the capability to do whatever treatments that you need. So obviously there are many limitations, because you may be a lot of groundwater that you have to pump out to do the treatment. It could be quite costly. It could take many, many years to do this. So for example, like the Love Canal has been running more than 10, well, probably 20 years at this point, at least, to do the treatment there. So, whoops. So let me just, going the wrong way here for a second. Yeah, so basically you have to do the monitoring. And so you might have a sharp decrease initially, but then you might have a bit of an increase and so on. So you have to, the concentration might go up and down over time. So yeah, so also you could do like a soil flushing. So you could actually inject certain concentrations of different chemicals into the contaminated area and then extract this contaminated area. So the idea, you would increase the movement, basically the pump and treat, you can have some kind of contaminants that can come out, but if you add various chemicals to this process, maybe you can increase the solubility of these contaminants, and so then that could increase the rate of contaminant recovery from this area. So you could add various, change the pH or change the concentration of the contaminants, add various surfactants, add pH adjustments, add acids, add bases, add even steam, things like this that can, you can change the temperature. So all of these can increase the rate of recovery of your contaminants. So that's exactly what I just said. And you can inject water, other agents, chelating agents, all sorts of solvents, depending on what type. So you always have to cater the remediation method with the type of chemical that you're trying to remove. So, once you know what it is you're dealing with, then you can design what kind of remediation that you would be doing. Yeah, so this is the type of thing you can spray in different things. You can let it get to the groundwater, then recover this groundwater, extract it, bring it to the surface, and then do your remediation on the surface. Ultimately, you would like to have a good cleanup there, and then maybe you could actually do it circularly. You could re-inject some of the the solutions, and you could keep on with the process like that, so that you don't have to use too much water. Yeah. Okay, so electrokinetics is using a bit of a voltage into the soil. So you could put these electrodes directly into the soil. Your contaminants will move in response to the chemical potential. So and then the water will move according to the hydraulic gradient, of course. And so basically this is the schematic. So you have your positive anode and your negative cathode. And so any positively charged components in your water will move towards the cathode, and any negatively charged will move towards the anode. And so then you can recover, using the process fluids and so on, you can recover the solutions. And yeah, so you use a certain amount of electricity, obviously, to do this. So you have to design the exact spacing, the type of solutions to use, the type of electrodes to use for this type of thing. So that's one. It's kind of, it's used to some extent, but maybe not highly. You know, it is commercial, but it's not used in a lot of processes. It's electric because you do need energy for this type of process. So as I initially mentioned, you can use impermeable beds and walls to stop the flow. But what you could also do is use permeable beds to actually to absorb the contaminants in the groundwater. So this is another approach. So in this case, you're actually treating the water because you're allowing the groundwater to pass through this barrier, but using the barrier to do absorption, say, for example, using activated carbon or an ion exchange resin or using non-zero valent iron, things like this. You could pack the wall with this type of material, and so all your contaminants would then be absorbed into the wall. So depending on your contact time and depending on how fast it is to plug, then you have to take these into consideration with how much contaminants that you have. So you might have to replace the wall over time, sorry. So you could direct the flow into a certain area using a funnel and gate type of system. So this is kind of forcing all the groundwater through this area. So this is another approach. And as I say, this was developed by the University of Waterloo in Canada. So yeah, so you develop the permeable material. It has to be permeable enough. You have to be able to remove your contaminants. And ideally, if you could do a regeneration of this material, that would be the best. So as I say, you can do these funnel and gate type of systems. I don't know what I have. Let me go. Oh, maybe I removed it. Okay. Anyway, no big deal. Okay. Yeah, so basically the funnel and gate type of systems, you're just forcing the groundwater through a specific area, and you have this bed to allow the contaminants to absorb. So this is the idea, like you could have this, as I say, the permeable reactive barrier, and then your contaminants would pass through this barrier and would absorb your contaminants over time. So obviously you need to have a set of monitoring wells to see exactly what you're dealing with. Yeah, this is just underneath a landfill. So obviously, if you're going to design a landfill, you have to have the proper mitigation to ensure that the contamination is not going to get into the groundwater. So ideally, you would have to have a set of barriers underneath your landfill to recover the leachates that are produced in the landfill, and then to have a set of barriers, as I was saying, basically geomembranes and so on to protect any leaking. And then ultimately you would like to have an engineered clay barrier underneath. This clay barrier would be the absorption of your contaminants and would protect your groundwater. So yeah, so you can have many different types of treatment processes. We've started looking at some of them that are based on absorption. But you can have all sorts of ones like air stripping, bioprocesses, which I think we will tend to get to a little bit later. And you could also have different processes in different steps. So I think I will, this is more in the soil, but what you can do is also, if you have say, for example, contaminants that are very volatile, you could force air through the soil and then force the contaminants to volatilize and then try to capture the contaminants that are volatile and then do a process whereas you capture the contaminated air and then do the treatment of the contaminated air via a biofilter or an activated carbon system, something like this. And so that way you can be assured that when the air goes out, that you have no contaminants in the air. Yeah, okay, so it's just back onto my funnel and gate system. It's a little bit, picks up a little bit, but anyway, this is back to the funnel and gate. And the type of contaminants that you have. So you would have to build it in terms of the depth, the width, and all of these type of things, what kind of permeability you want. And obviously it has to be compatible with the type of contaminant that you have. I don't know why. Anyway, so I had mentioned that arsenic can get into groundwater. I think as the very end of one of the slides at the other section. So arsenic in groundwater is a big issue because it's very toxic. It causes cancers and skin cancers and so on. So normally the concentrations are very low. So you'll have to have very effective processes, but sometimes they can be generating waste streams when you're doing the processes. So you want to try to avoid creating another problem if you're trying to treat your water, but you don't want to be generating other waste that then you'll have to deal with. So this is kind of the message in this table, and kind of, you know, when you're thinking about the treatment, try to think about everything involved in that treatment. Are you going to have to treat the air? Are you going to have to treat side streams? Are you going to be creating sludges? Are you going to be creating other problems to do with the groundwater and things like this? So you have to think a little bit more globally. Are there you know, are you going to have to regenerate some of the resins? So that might create another liquid stream that you have to deal with. Are you dealing with membranes? Maybe you have to look at regenerating the membranes and so on. So yeah, so dealing with groundwater quality, you want to make sure that you have sufficient quantities of your groundwater. You want to make sure that your quality of your groundwater is really, really good. So if you have the sufficient quantity, you want to make sure that the quality is okay. If it's not, then maybe you have to do some treatment. If, you know, are the structures in place? If not, then you have to think about doing the treatment. If it's already good quality, then you could directly use it, obviously, for drinking water. If not, then you might have to put some treatments in. So yeah. So ultimately, actually, you would like to get rid of any of the sources of contamination to begin with. So if you have to do the treatment, try to eliminate the sources of contamination. It's the best thing to deal with in the first place. So say, for example, you have your underground storage tank that we had mentioned before. Try to remove that underground storage tank that's leaking. So because you don't want to be continuing treating something if you don't have to. It's like, let's try to get rid of the source of your contamination the best we can. And that way you could, you know, ensure a good quality over time. You can use some models and things like this to ensure that you have sustainable water use, and so to get a good water quality plan. So if you want to look at mitigating strategies for contaminated soils and groundwater, you have to do all of the analysis, basically, try to make sure that you have the good soil quality, look at what byproducts are being produced, what are the costs, what is the short and long-term effectiveness of their various systems? Are you reducing the toxicity of your water or not? Are you having other byproducts that are produced that could create leaching and so on? And how stable is it under various environmental conditions? And so you can use various tools such as leaching tests, desorption tests, bioavailability tests, plant uptake tests, and so on to do these evaluations. So this does show like a bit of a quick comparison of various remediation technologies for groundwater. So as you can see, the containment, which we mentioned before, is just the barriers. So you're not really doing a remediation. It's just, you're not reducing the toxicity, but you are reducing the mobility because you're just basically putting up blockages and stopping the flow. I haven't talked about solidification yet, but we will. So you can add various components like cements and things like this, and this could reduce the leaching. This works usually pretty well in the long term. It does reduce some of the toxicity because that's the whole point, and it does reduce the mobility. Vitrification we haven't talked about yet. Oops, sorry. Biological treatment we will talk about a little bit in the future. Store washing we just mentioned a little bit. So usually the costs are pretty high because you're adding chemicals, you're pumping, you're so on. So these end up to the costs. They can work very well in terms of the long-term effectiveness. You can be reducing some of the toxicology, although it's not a big. The contaminant could be still there, and actually you're trying to enhance the mobility, so you're not really reducing the mobility of your contaminants. But that's the whole idea of what you're doing. The soil vapor extraction, which is the injection of the air, actually works pretty good in terms of the long-term effectiveness because you are removing it from the soil. It can't go back into the soil. You are reducing the chemicals, so you're reducing the toxicity, and you're inducing the mobility so that you're reducing anything that's easily mobile. Actually, that's the whole idea. You're basically extracting it using the oil, the air, and so you're doing a good extraction. So it works pretty well, and actually it's been pretty popular using the soil vapor extraction type method. The electrokinetics, which we just mentioned, is kind of an average in the cost. Depends on the electricity costs in the area, because that's the major costs, and the replacement of the electrodes and so on. Those are the two major costs for electrokinetics. It can work. Maybe sometimes the mobility reduction is not so good, and sometimes the toxicity reduction maybe not so good. But yeah, so these are some of the, these are some of the things that you need to think about if you're trying to choose which method to use for doing the remediations. So ultimately, you want to protect the water, so you want to have a good groundwater quality. So that's ultimately what you want to do. Things are changing a lot with the climate change, with the different rain patterns, with the different precipitation, the flooding, all sorts of things are changing things how to do. So it makes prediction a little bit more challenging at this point regarding water. If you're trying to choose what kind of remediation technology, you have many things to consider, such as the soil that you're dealing with, the permeability of the soil, the type of contaminant that you're dealing with, the properties of the contaminant, and so on. Whether it's volatile, whether it's volatile, whether it's soluble, all of these things will make you choose which type of remediation that you're going to be using. Ultimately, of course, the cost is always, and of course, whether it's going to be effective at that particular site or not. Sometimes maybe the technique that you're using may be good, but maybe maybe you need to work for a short time, then maybe you have to shift to a different type of technique depending on what the characteristics are at that site. And depending on sometimes you have a mix of contaminants, which makes things even more complicated, because if you have one contaminant, you can target that particular thing. But if you have a mix of all different types of contaminants, maybe heavy metals with organics, then that can make it even more complicated to deal with. And maybe you have to deal with different types of, you might have to target different types of remediation for the different types of methods. So yeah, so I think I will leave it at that for the break for the lunch, and we will come back in a little bit unless you have some questions.
Okay.
Yeah, you have questions or comments?
If there is any online comments.
Yeah, sure. If you have any online comments, otherwise you can think about it over lunch.
Like the water part is more easier for people to get.
Yes, it is definitely more easy. Yeah.
We are taking a break here.
Yeah.
And we will get back at the course will get back at 2:30.
2:30. Okay. So
今天上午的课程就暂时到这里，然后下午是2点半开始，然后线上的各位老师和同学也可以继续参与。